Okay, now, optional for Math 177 students, but I think worthwhile. We're going to prove something. Okay. Now, this is a fairly complex statement, so we proved it. In R2, meaning in two-dimensional space, so that our vectors have, two components. We want to prove that if V1 is a multiple of V2, then there exist vectors V, which are not linear combinations of V1 and V2. Okay? So, that's a kind of a big statement for anybody, in their first semester of college, which many people are. Big statement to digest. So you got to take it apart. You got to look at it carefully. So we look for phrases that can be interpreted. We don't try to interpret the whole equation or the whole statement. We don't try to understand the whole statement. Now we read it, and if we understand it, great. And eventually, by working on understanding statements of this nature, we get better at it because we learn what to look for. And what you need to look for is statements that can be put into mathematical form, okay, phrases. Okay, so let's take this, okay. The first condition is that V1 is a multiple of V2. Let's forget about everything else. What does it mean for V1 to be a multiple of V2? Well, V1 is a multiple of V2 means that there exists a number k such that V1 equals k V2. Okay? That means the only way V1 can be a multiple of V2 is if there's some number to multiply by V2 that gives you V1. We don't know what V1 is. We don't know what V2 is. We don't know what the multiple would be, but we can give it a name and we call it k. Use the symbol k for what we multiply by V2 in order to get V1. We know something multiplies V2 to get V1, so all we do is give it a name. Okay? We know something times V2 is V1 because a lot of mayhem in the hall for a late afternoon. Okay. People having fun, no problem. Okay. So we know that there's some multiple, there's something you can multiply by V2 to get V1. We just give it a name and call it K. Okay. Now these symbols, this symbol here means there exists. This symbol means such that. So this says there exists K such that V1 equals K V2. Now, we've got V1 and V2. We might as well give them names. Now, what I'm doing here isn't the most elegant way to do this proof, and I'll follow up by saying exactly what I mean, but everything we're doing is valid. Some of it's a little unnecessary, but we want to talk about the process of interpreting phrases. So we have vectors V1 and V2. We should give them names. So we're going to call V1 A1, A2, V2 is B1, B2. So now we say there exist vectors V which are not linear combinations of V1 and V2. I don't know what to do about V yet, but I certainly can write down a linear combination of V1 and V2. And maybe I don't think to give V1 and V2 symbolic representations until I see this and say, okay, I got to do a linear combination. I know what I got to do with that. Okay, so one way or another, you write down names for the components of V1 and V2. You can use that. You could use A, B, C, D if you wanted to. You could use alpha, beta, gamma, delta. You could use phi, phi, pho, fum for the components of V1 and V2. Now, those are all letters of the Greek alphabet, aren't they? Okay, well, according to Grimm, maybe. Okay, linear combination of these two vectors, whatever you call them, is going to be typically C1 V1 plus C2 V2. Now, to write out that linear combination, we need names for the components. So I've used A1, A2, B1, and B2. So we get C1 times A1, A2 plus C2 times B1, B2. If you want, it could be C1 times phi, phi, and C2 times pho, fum. However you write down pho and fum. But this is why I chose it. And clearly, having written down this linear combination, we see what we do with it, just the same thing we did in the problems that we did earlier. We add up those multiples. So, yeah, skip a step here, but we get C1A1, C1A2, C2B1, C2B2. And that gives us C1A1 plus C2B1 and C1A2 plus C2B2. So that's our linear combination. Now, I say that, okay, well, there's a condition. We haven't used this condition yet. And the fact then that V1 equals KV2 means that now with this representation, A1, A2 equals K times B1, B2. And that tells us then that, well, this is KB1, KB2, so A1 has to be KB1, A2 has to be KB2. So we conclude A1 is KB1, A2 is KB2. So now our linear combination, which was this, becomes what? A1 is going to be replaced by KB1. Okay? A2 we replace by KB2. There's our linear combination. Now, we can do a little algebra to simplify that. We notice that we have a B1 common to these two terms, so we factor that out. And we get C1K plus C2 multiplied by B1. And then we factor B2 out here, give C1K plus C2 multiplied by B2. And then if we're alert, we notice that this is the same as this, so that we can factor this out of the whole vector and write the vector as C1K plus C2 times B1, B2. Okay. Now, this vector is a multiple of B2. And this is the form any vector has if V1 is a multiple of V2. For some K, the linear combination comes down to this. What does that leave us? Well, this is a multiple of our vector V2. Okay, so this is C1K plus C2 times V2. I'm just going to state there are vectors what ain't multiples of V2. Not every vector in R2 is a multiple of V2 because V2 is confined to one direction. Take a vector in any other direction, it's not a multiple of V2. But under these conditions, any linear combination of V1 and V2 is a multiple of V2. So there are vectors that aren't linear combinations, there are vectors that you can't get as linear combinations of V1 and V2 if V1 is a multiple of V2. So now down here I don't say all that, I just say, well, there are vectors what ain't multiples of V2. Okay? That should be obvious. V2 is just one vector, it has just one direction, there are vectors in other directions. So we're done. Why are we done? Because this is what our linear combination has to come down to under these conditions. Okay, so try to digest that. And then think about how I could have done this a little more elegantly. There are a couple of steps here that didn't really have to be written out. We could have kind of gone directly to this form here. Okay? So I'll talk about that briefly in a minute.